Hello and welcome back to the podcast. In this episode, we're going to be talking about the equilibrium constant and how to use it. The equilibrium constant is given the symbol Kc. That's an uppercase K with a subscript C. And in this episode in particular, we're going to be talking about the homogeneous aqueous phase equilibrium constant. That's the one that you'll probably need to use the most. There are other ways of calculating Kc when not everything is in the aqueous phase, but we're going to deal with just the aqueous phase today. So what's the equilibrium constant and what's it for? Well, it helps us to quantify the position of equilibrium. Until we start using the equilibrium constant Kc, we can only talk qualitatively about the position of equilibrium. Also, the equilibrium constant is a constant at constant temperature for a particular reaction. So if we're performing a reversible reaction, we've reached equilibrium at a constant temperature, and then we change the temperature and allow the equilibrium to restabilize itself, reestablish itself, then there will be a different equilibrium constant. Equilibrium constant will always change with temperature, and it will always remain constant if temperature is not changed. Speaking of equilibrium, we can only calculate the equilibrium constant when the reaction is actually at equilibrium, i.e. it's in a closed system at constant conditions and has reached equilibrium. In other words, forward and reverse reactions are occurring at the same rate and there's no net change in the concentration of anything present. As we go through this episode, it will become apparent that you need to know the balanced chemical equation of that reversible reaction if you're going to calculate or even use the equilibrium constant. So I've just talked a little bit about the position of equilibrium, and I talked about that in the previous episode too. What does position of equilibrium mean? Well, it's a statement, an indication of whether the forward or the reverse reaction is favoured in a reaction. So when the forward reaction of a reversible reaction is favoured, the position of the equilibrium is said to be on the right. In other words, the net position at equilibrium is that most of the reactants have become products. There is less reactants left than there are products formed. If the reverse reaction is favoured, the position of the equilibrium is said to be to the left. And in that situation, the net overall effect is that most of the reactants are still reactants. Not much has become products at equilibrium. So in order to use the equilibrium constant, we need to write the equilibrium constant expression. We need to know the balanced equation between reactants and products, the stoichiometry. We also really need to know what states each of those are in. Are they solid, liquid, aqueous, or gaseous? So let's consider an example. Now, example, substances A and B react together, and the product is substance C. The reaction is reversible, as you'll see with the bidirectional arrow, the reversible arrow, showing that it is a reversible reaction. In this example, substances A, B and C are all in aqueous solution. The stoichiometry is that X moles of A and Y moles of B react together and give Z moles of C. So the equilibrium constant Kc is equal to the concentration of products individually raised to the power of however many moles of each of the products are present in the balanced equation, divided by concentration of reactants individually to the power of however many moles of each reactant there are in the balanced equation too. Let's look at an example. We're going to look at a generic example first, where substance A and substance B react together and give substance C. It's a reversible reaction. All the substances are in aqueous solution, and the stoichiometry, the balanced equation, tells us that X moles of A and Y moles of B are reactants, react together, and Z moles of product C are formed. So this is how you establish the expression for the equilibrium constant for this generic reaction. Kc is equal to the concentration of the products. We have just one here, so that is C. to the power Z, whatever Z is the number of moles of C in the balanced equation. And that value is over the concentration of A to the power X. X was the number of moles of A in the balanced equation, times the concentration of B to the power Y. Y being the number of moles of B in the balanced equation as well. You'll notice that we've written concentration of A, concentration of B, and concentration of C in square brackets. The square brackets merely mean the concentration in moles per decimeter cubed of that substance. If we know the concentrations of A, B, and C, and we know the balanced equation, so we know what X, Y, and Z are, we can put those numbers in, we can do the calculation, and we can come up with the value of Kc. How about actually if we started with substance C and we didn't have A and B to start with? Because we know this is a reversible reaction, we know that C will start to produce A and B immediately. Effectively, we are setting up the same equilibrium. And of course the reaction will come to equilibrium at some point. Let's say we're doing it at the same temperature as when we started with A and B. Will we have a different Kc or not? Well, we will, and we will because the expression for the equilibrium constant is different. It's the other way up, if you will, because in this version of the reaction, in this experiment, we've started with C rather than with A and B, and therefore A and B are the products. We didn't start with those. They are produced, they are products that were made during the reaction. So let's write the expression for the equilibrium constant when considering the reaction starting with C. In this case, we're going to write Kc is equal to the concentration of our products, which are A and B. A to the power X, because the stoichiometry is the same, it's still X moles of A that are in this balanced equation, and B to the Y, it's still, of course, Y moles of B that are in this balanced equation, and this is all divided by the concentration of the reactant, which was C, to the power Z, however many moles of Z there were. So you can see the equilibrium constant in this case is the alternative way up from when we started with A and B. And it's simply because we're considering, in this case, C to be the reactant and A and B to be the product, because we actually started with C, so it was the reactant. Let's consider a real example, an example that you may have come across in the lab, or you've at least come across in the textbooks, I'm sure. This is the reaction between ethanol and ethanoic acid, giving ethyl ethanoate and water. Okay, so you might know ethanoic acid as acetic acid, and you might know ethyl ethanoate as ethyl acetate as well. So because we started with ethanol and ethanoic acid, those are our reactants in this case, and ethyl ethanoate and water are our products. And we can see in our balanced equation that there is 1 mole of each reactant and 1 mole of each product. To write the expression for the equilibrium constant, Kc, this equals the concentration of ethyl ethanoate times the concentration of water, both to the power 1 because there is 1 mole of each in the balanced equation. When it's just 1 mole, we don't write that 1 in. It doesn't mean anything when it's just a 1. If it's any other number, you do write it in because it does make a difference. And on the bottom of the expression, we put the concentration of each of the reactants, ethanol and ethanoic acid. Again, there is 1 mole of each in the balanced equation, and we don't write to the power 1 for exactly the same reason that we don't for the products. Now we have that. If we had the concentrations, we can put those in to do the calculation and come up with the value of Kc. So you may be wondering about the units for the equilibrium constant, and I'll go into a lot more detail in another episode about that. In short, there isn't a fixed unit for the equilibrium constant across all reactions. The units for the equilibrium constant for each reaction have to be calculated, have to be derived in each instance, and it depends upon what the balanced equation is. In short, when you write out the equilibrium constant expression and you put in the units on the top and the bottom, if you cancel those down, whatever you're left with is the units of the equilibrium constant for that reaction. Like I say, we'll go into more detail in another episode. Also, it's important to remember that what we've talked about today, what we've just gone through, is relevant if the reaction is in the homogeneous aqueous phase. In other words, all the substances, products and reactants are in the liquid or aqueous phase. If you've got solids or gases present, it makes it quite different as well. And actually, the equilibrium constant expression would be different in those cases too. So once we've calculated the equilibrium constant, what does it tell us? Well, without the equilibrium constant, we could only make qualitative statements about where the position of equilibrium is, and whether it's to the right or to the left. But once you've quantified the equilibrium constant, you can actually quantify that. Because of the way that the expression for the equilibrium constant is, if the value you calculate is significantly greater than 1, that means there is more product than there is reactant at equilibrium. And that tells you or confirms that the equilibrium position is to the right and that the forward reaction is favoured. If the value for Kc is significantly less than 1, that tells you that the equilibrium constant is well to the left and that there is more reactant than product present at equilibrium. And the final thing to talk about is what happens to Kc at equilibrium when we change the conditions, and specifically when we change the temperature. If you go back to the last episode and listen to that, you'll remember I talked about Le Chatelier's principle. Le Chatelier stated that if we change the conditions of a reaction, if we disturb it, the position of equilibrium will change, and it changes in a way that tends to reduce the effect of that disturbance. So if a reaction is at equilibrium and then the temperature is changed, that principle tells you that the position of equilibrium will move. It will move to reduce the effect of that temperature change. Once the equilibrium is re-established in its new position, if you were to measure the concentrations again and calculate Kc, you'll find that Kc has changed. In fact, temperature is the only condition that changes Kc. And if you change temperature, you will definitely change Kc. You will definitely change the equilibrium constant. Changes to concentration or pressure may change the position of equilibrium, but they won't change the equilibrium constant. And remember that when you add a catalyst, you don't even change the equilibrium position, so Kc certainly doesn't change either. Okay, I hope this has been really useful. What's the biggest takeaway about the equilibrium constant that you got today? Write it in the comments, please. And also put in there about any particular questions you've got about the equilibrium constant too. Just want to say a thank you for the patrons who are supporting this podcast. I really appreciate you. If you're not a Patreon supporter yet, you can do so at patreon.com/chemistrymadesimple. It would really be welcome and helpful. Thank you. If you have any more questions or ideas about what you'd like to see in upcoming episodes, then please do contact me. You can do so at my email. That's matthew@chemistrymadesimple.net. You can leave me a short voice message at chemistrymadesimple.net/voice note. And I really look forward to hearing from you either way. And I do get back to you. I look forward to seeing you in the next episode. And don't forget to subscribe so that you don't miss that. Thank you.